This is a pressure volume loop. It's just very generic, and usually there's these lines are a little bit more curvy, especially here and here, but I just kind of used the shape that was available to me in Microsoft Word. So anyway, this is the pressure volume loop, sometimes called the flow volume loop. And so a few things here let's go over. I actually recommend if you have a test question where there's a pressure volume loop aspect to it, it might be easiest just to draw one out real quick and try to figure it out on there and then answer the question. So anyway, first thing, the axes. What are the axes on the pressure volume loop? Um, you might, everybody kind of gets this a little bit confused, but there is no time on this. Where is time on the pressure volume loop? It's actually just going around this entire thing one time would be one heartbeat. So it really depends on how fast the person's heart's beating. So if it's beating 60 beats per minute, then going around this thing one time would be 1 second. So anyway, but time is not represented on the pressure volume loop. And as you can probably guess, pressure and volume are on here. So which is which? Okay. So this is volume, and it's generally in milliliters. And then the other axis is going to be pressure, and it's going to be in millimeters of mercury. And so let's go through it. So there's some different volumes on here. So the very first one that we'll talk about is right here, and this is the one that gets probably asked about the most. This is end diastolic volume. So a little bit counterintuitive, end diastolic volume, um, you're not thinking of the left ventricle when you think of that. This is all about the left ventricle though. This is a loop of the left ventricle. So what's happening is from here to here, you're filling the left ventricle. Where does diastole start? Okay, that's confusing. That's sometimes asked about. Diastole actually starts right here. So diastole, so this is going to be isovolumic relaxation because you can see here, here's volume. This is the volume axis. Volume has not changed. And so that's isovolumic relaxation. And at this point right here, um, so actually let me ask you this. What is the volume called right here that I just kind of circled in a little bit more, okay? It's called end systolic volume, okay? End of systole. Systole actually starts where? Right here, okay? And so that would be the S1 heart sound again, and then systole ends right here, and that would be the S2 heart sound, okay? So what's going on here is what had to happen, so you can see that now we're moving along the volume axis like this. So what had to happen right here at this point for the volume of the left ventricle to start increasing? What had to happen was that the left ventricular pressure went above, or I'm sorry, the left atrial pressure had to go above the left ventricular pressure, and the left atrial pressure is very, very low. And so the ventricle completely relaxes, and the left atrial pressure goes above, and then it starts to fill, and it fills, and it fills, and it fills, and you can see that the pressure is going up as it fills. And then at this point here, it stops filling. And why does it stop filling? Because the left ventricular pressure exceeds the left atrial pressure and the mitral valve slams shut. It makes that S1 heart sound, and then we have what? We have isovolumic contraction, and so the pressure in the left ventricle is going up. We call it isovolumic, iso, same, and you can see the volume, look, it's the same all the way up until this point here. And then what happens at this point here? Well, the pressure in the left ventricle becomes greater than the pressure in the aorta. And then after that, the next thing that happens is ejection. And so from here to here, you can see that the volume in the left ventricle is going down. We're going this way now. The volume's going down, but the pressure is going up. The pressure started here. And let me ask you about that too. What is the pressure right here called? You can call it, and there are exceptions sometimes, but generally you can call it diastolic pressure. You can also call it afterload sometimes. An exception to calling it afterload would be, and this is a little bit complicated, mitral stenosis. Let's see, but this generally is going to be afterload. So we have our ejection, then we have, we keep ejecting, and then we stop right here. And what happens again, these valves open and close based on pressures on both sides. So the pressure in the aorta is now higher than the pressure in the left ventricle. And so that valve closes. We get the S2 heart sound. That's the sound of that. And then this point is very significant and it's heavily tested. What is it called? It's called peak isovolumic pressure, okay? And so again, peak, we're at the peak. Isovolumic, it's same volume, the volume's not changing. You can see here that the volume is not going to change until here. So we're at peak isovolumic pressure. And what's so significant about that, this is a really important thing to know. This is a measure of contractility. There's going to be a line that you can kind of draw like this. And what that means is that for the same contractility, which is a future topic, you're always going to end on that line. So you could fill the ventricle more, you could make afterload more, you could change different things, but no matter what you change, unless you change contractility, you're always going to end up ending your stroke on this line, meaning that systolic volume will always end somewhere on this line. And that's a complicated thing to think about, but I think as you do practice questions, it'll make more sense. Let's see, so what else is there to know about this? Let's see here. We talked about, okay, so let's talk about this a little bit more because there was something I forgot to talk about. This is end diastolic volume. You can call it some other things. What can you also call it? You can also call it preload. You can also call it end diastolic pressure. And there's something that's related to this point here, and this is a little bit counterintuitive and it's a little far back, but the central venous pressure can be an index of this. It's proportional to it. It doesn't equal it, it's proportional. But let's see, other than that, this is a really good thing to know. This is just kind of an overview. You're going to want to be able to change different things at different times and understand the effect on the flow volume loop. You're going to want to understand what happens when you change afterload, when you change preload, when you change contractility, when you change heart rate, stuff like that. And those are things that I'll talk about in another video, but I hope this makes sense.